So I've been working in the UAV area for, I don't know, 15 years. And maybe I'll just use my slides to give an introduction. So I'm going to talk about vision-based navigation and tracking. And, well, this was working just a minute ago. Oh. Maybe it did work. Okay. So I thought I would just give a little bit of an introduction to our lab and some of the things we've been doing, and then talk about two main areas of research we've been doing recently. And so some of the work, actually these are active research projects, so I'm not going to give like a complete, this is all finished and wrapped up type of presentation, but these are the types of things that we're working on right now. Let's see. There we go, it's just delayed. I have to wait. I think maybe I'll just use this. Okay, so this is a bit of a roadmap of things we've been doing. So I've been working in the cooperative control area for a number of different years, and then at some point we decided we wanted to actually fly vehicles, and so we were working in terms of path planning and trajectory generation. That's been an area that continue to work in. And then we actually developed an autopilot a number of years ago, and we've kind of gone through numbers of iterations of that. And then really the last, 5 or more years I've been working on vision-based flight. Okay, let's see. Yeah, these are some, across the bottom are some of the vehicles we've worked on, a lot of flying wing, but also tail sitters and multi-rotor type aircraft. And this is a picture we took, 3-4 years ago, showing a variety of different aircraft that we fly. Actually, a lot of the funding that we have right now is through this National Science Foundation Center for UAS, which is a university research cooperation. And I think, a lot of the work that goes on here is very similar in terms of being very industry centered in terms of, interaction with industry. Okay, so I guess I'm preaching to the choir in terms of UAS impact. There's there's lots of opportunities right now in the UAS industry, and it's kind of a fun place to be. It's also a little bit challenging because so many people now have jumped in, and so we're really there's a lot of competition. So this is in terms of the where are we going? What's the future? So there's really two areas that we see happening right now. There's all of the UAS work that's happening, and then there's also the self-driving car industry. And there's quite a group of companies now in the U.S. at least, I'm sure in Europe, who are developing self-flying cars or self-flying vehicles, right? That you could actually, I think that the immediate future is flying taxis, I guess, where you would go to a spot and fly from one spot to another. But actually I went and toured a company just this last year where they're developing a vehicle that you get on and fly, a single person vehicle. So this is the personal self-piloted aircraft is, I think, not that far away. We just have to get over some of the regulatory issues and safety issues, but in terms of automation and things, we're getting pretty close to that. So it's a fun area to be in. Okay, so to be able to get there, there's a number of different things that we have to overcome. So in terms of technology gaps, we really need to have safe and reliable flight, things that are robust to loss, for example, of GPS, and also increased capabilities in terms of range, payload, agility. So I'm going to actually talk about things we're doing in this area. How do we become robust with respect to GPS degradation, and then also robust tracking of targets, ground-based targets. Okay, so that's the two areas that I'm going to talk about. So I'm going to talk about GPS-denied navigation first. And we've the way we think about this problem is something in between, GPS completely available, which is something we know how to do, fly with GPS, And then what happens if GPS is completely denied? So we've been thinking, in the middle where GPS is occasionally available, but even when we get it, it might be intermittent, it might be erroneous. What do we do? How do we fly vehicles in this type of environment? So just to give an introduction to that, this is a video or a picture where we went and took an aircraft and just walked this path. So this orange path is, we know truth because we walked along the sidewalk. And then we just look at what GPS gives us. GPS gives us this yellow line. And so, even when GPS, and actually we had 4 or more satellites, so the GPS receiver said we were receiving GPS. So, it's not like this is a GPS denied environment, but even in that case, GPS is giving us these weird signals that aren't exactly accurate. Okay, so how do we maneuver and fly? Obviously, if you wanted to fly close to the building, that would be a very difficult environment to, that type of sensor doesn't help you a whole lot. And so what happens if you want to fly in these types of environments where you're close to bridges, you're close to buildings, you're maybe flying down an urban terrain? In that case, GPS may be actually coming in and out. Okay, so the way we've thought about this problem is to think about, how do we as humans drive or navigate in our environment? We obviously don't have GPS inside of our head, but we seem to do just fine. And so the way we navigate, it's kind of this local, global, back and forth. So in our heads, like for example, when I'm driving home from work, I have in my head a map of where my house is and how I need to go. And actually, then I see landmarks, and I sort of localize myself inside that map. And even when I come to Porto, like I was yesterday walking around and not knowing anything about where I was, really. And I was fine. I didn't fall down. Like, I was stable the whole time, right? So anyways, we do a very good job of navigating locally. So we had this kind of local, ability to navigate. And then in kind of the background, we're seeing landmarks, and we sort of put ourselves in the map. Even, if we have our phone with Google Map, occasionally we say, oh, okay, this is where I'm at. I'm trying to go somewhere, but I'm still navigating locally, and then sort of updating my understanding of the map. So this idea of sort of a local front end and then global back end is the way we've tried to partition the problem. So when we navigate, we think about, a local front end where you've got the vehicle, you've got, some sort of odometry algorithm. So in our case, it'll be a visual odometry algorithm. And then we're doing some sort of relative state estimation. So I'll talk about what I mean by that. And then all of our, kind of at the front end, it's relative path planning. We're avoiding obstacles. We're trying to maybe go to the next corner or whatever. And then we use that type of information to update, with maybe place recognition. So we see a landmark or whatever. And so we recognize, okay, I've been there, this is where I'm at. And so you have some kind of place recognition, perhaps GPS comes in, and we use that type of information to update our global map. But this, and then with that global map, we can do some kind of global path planning and pass that then to the front end. And the nice thing is this relative front end, all of this has to happen in real time. Things have to be stable. We don't want to be running into things in terms of an air vehicle, but this has to happen real time. But all of the place recognition, mapping, the things that are somewhat hard can happen in the global back end opportunistically. It happens as we get information, and this type of stuff doesn't have to be in the feedback loop where we might have stability issues. Okay, so the idea with the relative navigation. So now I'm talking about the relative, what we call the relative front end. So the way this works is when we start, we start with a coordinate frame. Okay, so when we start, so this relative coordinate frame, when we begin at time 0, we know we're at the position that we're in, right? So there's actually 0 uncertainty when we begin. So we know we're at, because we're not trying to localize ourselves with respect to some global map where there's going to be some sort of uncertainty. So in the relative map, there's 0 uncertainty. And then we begin to navigate, and we have some kind of odometry algorithm. So the odometry algorithm, this might be the truth, and the odometry algorithm will have some kind of localization error. And at some point, that error grows to a point where we say, okay, we're going to save that odometry information, and we're going to restart where we're at. So when we restart, we're going to move the map over to this location, and again, there'll be 0 uncertainty. So we're going to continually do this, basically change the coordinate system with respect to where we're navigating. And then we pass that navigation information to the back end. So this is an example of the state. And actually, we're not going to restart things like so if we have some kind of altimeter, we don't necessarily need to restart those states because those aren't going to be jumping at all. And also, if we have roll and pitch angles we can get from the IMU, so we don't need to restart those. But position and heading information, we actually need to restart every time we lay down a new coordinate frame. And this new coordinate frame, we don't need to do it at a particular time interval, but we're going to do it, for example, when we move and the image changes enough, or if we're moving a certain rate forward, then we're going to have to start and establish new coordinate systems. So this is kind of the idea. We start with a relative coordinate frame. We navigate, and then that edge, we actually use as our front end a visual odometry algorithm, and then we pass those edges to the back end, and then at the back end, we use OpenFabMap for place recognition to recognize landmarks or places we've been before, and then G2O to optimize that graph in the back end. Okay, so we've done some comparisons to other approaches. So for example, something we call pseudo-global, where you're always keeping track of your position in some kind of global coordinate frame, but yet your measurements are all local. Stochastic cloning, which is doing something similar, where you're keeping track of your global state, but also you keep track in the Kalman filter of these local states. And then robocentric frameworks, and then relative navigation. So this is just some comparison with things that we've done before. And by the way, so the interesting thing as you navigate, so if you do something with just, for example, an extended Kalman filter, so doing something like EKF slam, you keep track of your position and positions of things in the environment, and you're always localizing, you're always linearizing and forcing the uncertainty to fit a Gaussian distribution. And so any kind of EKF-based framework, you have these, the uncertainty is a Gaussian distribution. But if you think about it, you move from this position to this position, if you have any kind of uncertainty in heading, then, and let's say Gaussian uncertainty in heading, from this point then, you would move and you would have Gaussian uncertainty in heading. And so when you compound those things, the actual uncertainty looks something like these banana distributions. And so forcing things into, say, an EKF framework you lose essentially the essential characteristic of the underlying distribution. So our framework actually retains that, because in a relative framework you do things locally that are Gaussian, but then as you compound those over multiple different frames, you get Gaussian, or banana-like distributions. So anyways, these are some examples of this. In this particular simulation, black was the truth, and then these are the different types of estimators. And at least, ours has this banana distribution that still includes the truth in its uncertainty bound, whereas, these other different frameworks, you're inconsistent in the sense that you don't lie within that. And these basically show that, we have consistency for this relative navigation framework. And it all comes from this idea of compounding, locally Gaussian distributions that are compounded as opposed to a global distribution that you maintain over time. Okay, so this is the type of thing you get with real truth data. Again, this is the truth, and at least our framework. We can do it both in inertial frame or body frame relative navigation. Still, at least, is consistent. Whereas all of these other types of methods lead to inconsistent solutions. Okay, so this is a video. I'll just play this for a minute to show you the type of environment we're in. This is the Student Center at BYU. The interesting thing about this environment is all the hallways kind of look the same. They're all kind of, so the updating global position is actually an interesting case. So if you fly this around this hallway multiple times with visual odometry only, this is the type of situation you get. So obviously you get drift. This is actually, I have another presentation I could give about the multiplicative. We have a relative multiplicative extended Kalman filter in terms of how we do the frame-to-frame localization. If you use that, you get a little bit better. And then if we add into that place recognition, so now as we move around, we say, okay, so anytime there's a red line, we say, okay, I've noticed that I've been there again, been there before, using this open FabMap framework. And so when you do that, after optimization, you get a much better environment. And then, what happens if occasionally you say, I think I'm really here, but I think I'm there. You get this, it really messes up the optimization. So we have a method for how do you handle those types of situations using this virtual zero. I think I'm not going to talk about it unless there's questions, and we can talk offline. We've also done some work on multi-sensor fusion. So if you have, for example, the platform that I just showed you has an RGBD sensor on it, and we're actually also flying a Hokuyo laser rangefinder. And those two sensors work in different, work well in different environments. If the light goes out, of course, this has problems in terms of RGB, but it still gives you depth information. And the laser rangefinder works pretty well unless you go into, an environment where the walls aren't very close together. And so we have this. The way we handle multi-sensors. Sensors in this front-end, back-end framework, relative navigation framework, is basically. Let me go to the next. Where are we? So what we do is we lay down key frames with respect to every sensor. So you may have, as you have a visual odometry algorithm, you might have also a LiDAR odometry algorithm. And the idea is that we lay down relative key frames in terms of, the LiDAR, and then we do relative key frames in terms of the camera. And then those are, again, passed to the back end with all of the uncertainty, and the optimization algorithm then, puts those things together. And so we can get, this is an environment where we went into a dark room. So if you go into a dark room with RGB D, it's doing fine until it gets into this dark room, and then the estimate just goes crazy. With the LiDAR, or with the laser, we actually we don't have scale information, so it gets us somewhat bad information. And then with the multi sensors together, we can do much better. Okay, so this is a video that we did about a year ago. So the guy in the background, he's just a safety pilot, so he's not actually doing anything. So this is the RGB D sensors, and then you've got down here we have this back-end graph. We're showing at least the poses that we pass to the back-end graph. And so right now it's navigating through this environment. We're going inside, outside, so we're having to use these different sensors as we do that. So let's see, it just speeds up a little bit here. Okay, so we're about to get our first loop closure. So you'll notice when we get a loop closure, it rectifies the map a little bit better. But we still don't know where we are in the world. And so I haven't talked much about how GPS comes in here, but GPS just comes in as a constraint in the back end. So it just says, okay, this is where I'm at, and so we localize with respect to a map. So at some point here, all of these little yellow lines are loop closures from the vision or the LiDAR data. So when we get those loop closures, then we can pass that to the back end, and there's an optimization that happens. And then at some point here, we actually will get a GPS measurement when we go outside. So we're in between buildings, and so GPS is pretty flaky. So we're about to receive our first GPS measurement. And when we get a GPS measurement, we can actually localize ourselves. So now we're receiving several, it doesn't show up here, but there's a couple of little red things that say that we've received GPS. You can kind of see where the GPS sensor was active. And when that happens, we can actually localize ourselves in the world because we know the actual world locations. So this is actually not perfect because the doorway is right here. I guess that's after the final optimization. Here's the doorway, and I think the doorway is right there. So anyways, it's getting better and better as we go along. Okay, so this is also something right now, what we're doing currently is saying, okay, how can we extend that framework to a multi-vehicle scenario? And the idea is that the front end would run, this relative front end runs on every single vehicle, and then things pass to a global back end that is shared across the cloud, for example. So you would have a number of different relative front ends, and then the back end can be shared among vehicles. And we have, I actually, this is about a year old, so I was trying to find our most recent results. But we have some interesting results that are all in simulation right now with multi-vehicle, in the multi-vehicle setting. So anyways, in terms of how this works, so the relative navigation, essentially, you're doing things in a local frame where consistency and stability are essentially given because you're in the correct coordinate frame, and then this global frame sort of slides around behind you. And you don't have any, as you update your global map, so a lot of competing frameworks, when you update your global map, you get things like control jumps or estimation jumps. But here, things sort of slide around underneath you, and so you don't get any of those types of jumps in the state that you're controlling with respect to. And then multiple agents, we basically just have to communicate through the cloud doing this back-end optimization. Yeah, and any kind of state jumps from optimization don't result in controller estimation jumps. Okay, so that's kind of my talk is divided into two different parts. That's an update, I guess, on things that we've been doing on this GPS degraded navigation. I'm going to look at my watch and see. So I don't know, maybe should I take questions now on this part? Because I'm going to shift to sort of a different idea. Any questions? Yes? Yeah. And I guess you're talking about doing that at the back end. Yeah. So this back end optimization, yeah, I think that's a perfectly reasonable way to approach that, because you'd have this back end optimization where you say, you know, these are the actual physical global constraints, and so you would update. You know, right now we just have uncertainty bounds, and so the update is just bounded by those uncertainties. But you could put hard constraints in terms of, we know where the walls are, and, you know. Right. Yeah. Yeah, no, I think that's a great idea. We haven't done anything like that, but I think that would be a perfectly, in fact, that seems like a good idea to do in those types of environments. Oh, but the optimization is happening sort of in the back end, not EKF. Oh, you're saying in an EKF framework that would be more difficult. Yeah. Right. Yeah, I really like this low relative front end, global back end, because it allows you to do all sorts of things like that. You know, so in the back end, you could add constraints and just simply solve the optimization problem there. Yep. Yeah, good suggestion. Any other question? No, we aren't running any of the optimizations, right. Yep, all of that happens in the back end. So basically in the front end, so with visual odometry, you know, we have a camera, and you're essentially moving forward, and then as soon as, so you're tracking features, you know, in the video frame, and then as soon as those features start, as soon as a certain number of, or percentage of those features move outside the field of view, then we'll recreate a new frame. Or as you turn, you know, as soon as we turn, and again, features leave the field of view, we then establish a new framework. So, you know, that multi-rotor that I was showing you, about every 4, and it's moving relatively slowly, but about every 0.4 meters, so almost every half meter, we establish a new frame. And then as you turn, about every 30 degrees, we end up with a new frame. So you do have a lot of frames, but these that back-end optimization, the G2O, you know, you can actually have tens of thousands of frames, and it does a good job of optimizing. No, right. Well, the back end can happen, you know, as is. So if it takes us, right. So with about 10,000 frames, it takes, you know, a second or so to do the optimization. But then, you know, it basically is updating things that don't affect you in real time. So that's kind of the beauty of the framework. Yeah. Yes. Right. Yes. Right. Right. So no. So when you stitch them together, you're basically we basically have, you know, the state estimate and the covariance. And then we're going to stitch them together based on the covariance, essentially. So there's no model. So when you do the back-end optimization, yeah, that's a good point. There's no model of the vehicle that's constraining things in any way. Yeah, it's all based on the probability distribution around the state. Yeah. So I don't know. There might be things, maybe there are things you could do there that would make it a little bit better. Yeah, that's an interesting idea. Okay, any other questions? Okay, so I'm going to talk about the second, the robust target tracking. I'm actually pretty excited about this area. Okay, so I don't know. Oh yeah, here we go. Oh yeah, that's why I was doing it with my finger. Okay. All right, well anyways, this is a video that is motivating and somewhat, or motivated us a number of years ago in terms of looking at this problem. So we're tracking with video a white van, and the windshield looks black. And then we go over the top of a manhole that looks white with black. I don't know if you saw what happened. The video tracking algorithm gets stuck, and then it got unstuck. So what happened when it got unstuck was a human clicked. We're sitting there watching it, and we clicked and said, no, jump back, so that the video would look good, right? And the same types of things happen. So this is another, I have another video. Well, anyways, so this is something that is very common in terms of vision-based tracking. The user has to sit there and babysit so I'm sure you guys know, right? You have to babysit the tracking algorithm. And so our motivation in doing this work is to really try to reduce how much interaction the user has to have with the video to try to make things more robust. So we're really kind of playing at the intersection of three different communities. The multiple target tracking community, which has really in the past been radar based, and then the computer vision community, and then of course the UAS application community. All right, so I'm going to talk a little bit about what we've been doing in this area, and we have this new, I don't know if anybody's seen me give a talk on this before, but a few years ago we came up with this recursive Ransac algorithm that I kind of like, and so we've been playing with this algorithm, and we have a number of different things that we're using it for, so I'll talk about that. So this is the recursive Ransac. This is a new algorithm, maybe three, 4 years ago. Developed out of my group, and it really allows multiple target tracking where you have lots of clutter. It has a very fast data association mechanism that I'll describe, and really has some nice performance features like good track continuity and pretty robust performance in cluttered data. Okay, so I'm going to describe this algorithm, and so many of you, if you've had a computer vision class, you know what the Ransac, how many people know what the Ransac algorithm is? Okay, so some, but not everybody. So if you've had a class in computer vision, for example, you'll know what this algorithm is. So it's a very standard algorithm. It's about 15 years old and really had a kind of a transformative effect in the computer vision world. So the algorithm is really easy to understand, and so I'll explain it like in a least squares context. So suppose you have a bunch of data, and so the Ransac, the traditional Ransac algorithm is always run in a batch process. So if I have a bunch of data, but my data has an outlier, okay? If you run least squares on this data, of course you'll get a very bad solution, right? Because this one outlier can really affect the data. So what the Ransac algorithm does is it says, okay, if I'm trying to fit a line to this data, I need 2 points to fit a line. So I have this, I have a model of the data, and I have to have a minimum subset of data that will create that model. So in the case of fitting a line to data, the minimum subset would be 2 points. So what I'm going to do is randomly select a minimum subset of that data. So in this case, I would randomly select perhaps those 2 points, and then I look for inliers around that model. So in this case, the inliers might be, some distance from that line. And so this particular model hypothesis would have, 3 inliers. And then we randomly generate a new model. So here's a new model that actually, in this case, we picked the outlier, and that particular model hypothesis doesn't have very many inliers in it. And then we may randomly pick another 2 points, and that particular model has quite a few. So we do that a number of different times, and we'll finally get, and then we score each one, and after doing it so many times, we'll take the one with the best score. and then we may run least squares perhaps on that data. Okay, so now what happens? So that's the standard batch Ransac algorithm. So recursive Ransac is, what happens if you have data that comes in now sequentially. So what happens if you have a model, perhaps, and you get a new measurement, X here, that's coming in sequentially. So what do you do with that data? So I guess, what I'm showing here is you may do a Ransac model, and you get, so let's say you run Ransac at the beginning, and you get a model, okay? So these model parameters, we have the covariance matrix, and then the consensus set is all of the points that are inside of that model. Okay, so now what happens if we get a new data point? So this would be X down here. What do we do? So if that data point is an inlier to the model, we simply update the model, and we move on. If we get a point that's outside of the model, then we basically run another Ransac type algorithm, and we generate a new model that always, so when we pick those 2 points, we always include this as one of the endpoints, So we generate a new model that is consistent with that new data point. So now we have 2 models. And this model may not, they may not match, but at least the second model is consistent with that new measurement. Because we don't know if all of these points are outliers, and the one that we just received is the only good data point, right? So the only thing we can do is keep a couple of models around in memory. So then if we receive another data point that's not consistent with either of those 2 models, well, we would have to do a Ransac process and including this data point and generate a new model. And then we can continue that. We may end up with multiple models. And then over time, we get data points that maybe are consistent with 2 of the models, but not really with these other 3. So then we could prune models that don't have a lot of data points and continue to move on. Okay, so this is that's basically the algorithm. And so what we do now is, so in computer vision, I guess let me just go back. For the Ransac algorithm, it's typically used in, for example, tracking, frame-to-frame tracking. So you'll have a whole bunch of data points in one frame and a bunch of data points in another frame. And if you have you match 5 features, you can find a homography matrix that basically maps one frame to the next. Okay, so your minimum subset would be 5 features that match, and then you could look at all the other features to see if they map through in a correct way, and you could score the algorithm. So that's basically the way Ransac is used in computer vision, is to basically find frame-to-frame matches. And these matches are very, you get lots of feature points in one image that map to the wrong features in the other. So the Ransac algorithm is a really good way of culling through and finding, the correct homography from one frame to the next. Okay, so what we're going to use for tracking is we'll use a Kalman filter as our model. And we'll have some with an underlying motion model, so a constant velocity, constant acceleration, constant jerk model, and we basically can then generate trajectories. And so we're looking for, instead of a straight line fit, we're looking for trajectories that match the underlying data. So, for example, this video shows you. So orange, everything that's in orange or yellow is a track that is being generated from the video data. This data is actually, so what we're doing is we're taking frame to frame, we're just doing background subtraction. So motion is detected in terms of anything that is that shows up when you do background subtraction. And then given that data, we generate models. And so you see all of these little orange models, and these are models that get generated in the recursive Ransac algorithm, but then they don't have, if they don't have a lot of inliers, then we don't turn them yellow in terms of, we don't believe it's a good track. But after we get a number of different inliers that match, we turn those yellow and assign a track label to them. So this is kind of showing what's going on with video tracking. And this actually works pretty well even in really crummy video. So this is a low light, we're on a UAV, we're flying around, we've got people that are walking around in this field where there's snow and background, and it's kind of amazing really that we can pull the tracks out of this type of video. So it works really well in these types of environments. And video, most video is, you have lots of outliers. So it's this frame, it's basically this setting where you have lots of garbage that's going on. And we've actually flown this with radar as well, so I'm not going to talk about this at all, but radar measurements, it's the same sort of thing. You get lots of clutter in the radar, and so this is we were doing some sense and avoid, a project with sense and avoid where we've got 3 aircraft out here that we actually use the recursive Ransac algorithm to generate trajectories, and then we do a collision avoidance thing. So anyways, it can be used in settings where, it's not just video data. Okay, so let's see. So I have a number of different slides now that describe kind of things that we're doing with it. So the first is, what do you do in terms of a UAV? Now you have a moving, you have moving targets on the ground, plus you have a moving camera, right? So you have to pull out tracks where you've got ego motion, but also motion due to the targets. So we have a couple of different things that we've tried. And I guess the simplest idea is, going back to background subtraction. So if the camera is separate, you can just do you take one frame, then you take the next frame, subtract the 2, and anything that shows up when you subtract the 2 has to be moving. So what we do if the camera is moving is we have a frame-to-frame tracker. So using this homography tracking, so Ransac to compute homography. So you go one frame to the next. You can use a traditional Ransac algorithm that gives you the homography matrix, which maps pixels in one frame to pixels in another frame. And so we basically are always using that to push old frames into the current frame, where we do background subtraction and then track everything that's on top of that. Now the problem is that if you have trees and things the homography computation assumes that everything is coming from a planar environment. So if you have non-planar environments, then what happens is you get lots of stuff showing up, you get lots of clutter. And so the recursive Ransac algorithm then is pretty good at throwing away all that clutter and just keeping track of things that actually are moving, or at least behave like a constant velocity, constant acceleration model. Okay, so that's kind of the idea. You get lots of, in frame to frame, you get lots of features that show up, but over time you can really find the features that so lots of features are showing up when you do this frame-to-frame subtraction, so you can see all the green features that show up. But those essentially, don't move. Once you push everything into the current frame, they don't look like constant velocity or constant acceleration or constant jerk model. So you can do a pretty good job of pulling out the things that are actually moving on top of the camera motion. Okay, so track continuity. Oh, this is, so let's see. So I need to be done at 7:15, 7 or 10:15, 10:30, 10:30. Okay, so I have, all right. So I have plenty of time. Okay. All right, so yeah, there's a variety of different things that we can do in terms of so what we call the front end and then the back end part of this process. So the video comes in, and then we have to do something to pull out features. And then once we have features, we can do this recursive Ransac algorithm and generate tracks. So we can do things like feature motion, where we're basically we find a whole bunch of features in the image, and then we look at how those features move. And then we can use that feature motion directly and maybe look at what most of the features are doing and say that's going to be background information, and then subtract that off of the rest of the features and then look on top of that. So that's one particular way in which we could try to find moving things when the UAV is also moving. And then difference image, that's exactly what I just described. And then some kind of direct template matching where if we can somehow figure out, oh, okay, that's a moving target, then I'm going to just do frame-to-frame template matching around that target. So what's the best? And in that particular case, we have to initialize. We can't initialize them automatically. These methods allow us to initialize the track automatically. But here, we may be able to do much better long term, but we can't really do it automatically. Yes? Yeah. You do see a lot, like, yeah, you're seeing, oh, well, let's see.
Why don't you see that change in that dark areas right there? Those dark areas like a shadow.
Right here? Right here?
Why don't you see that image on? From frame to frame while you're moving, you would think that that's an object. Or that other object over there, that other shadow, or changing the asphalt on the left there. That's what I do. You can see those features.
Yeah, I guess we are right there. We are seeing some of them, but maybe not. Yeah, so what's showing up here are when you do frame to frame and then you do the background subtraction, yeah, we're just plotting what's showing up. So I don't know. That's interesting why some of those aren't, some of them actually get subtracted out, but some of them don't. And we only, I guess they have to show up to a certain level before we're plotting them here. Yeah, I guess the interesting thing is that you do have all these things that are showing up that aren't really features or aren't really things that you're trying to track. And then the recursive Ransac algorithm, that's where it really shines in terms of pulling out things that really are moving with respect to some motion model. Yeah. Yes. Yeah. So what's happening here is that's a good question. So when we do frame to frame, everything that shows up as a potentially moving target is in green, plus a bunch of stuff here that we're not showing. Okay, and then once those green things show up, then we fit motion models to those. Okay, so the recursive Ransac algorithm fits motion models to them, and those would be like those little orange things that are. So I'm not displaying that, but after we then pull out only the good tracks that have good support, then we put a yellow box around them. Yeah, so this is kind of after that recursive Ransac algorithm has processed the data. Yeah, I'm glad you asked that. That's kind of a maybe confusing video. Okay, so so we have these different ways of trying to figure out moving things. And so one area, I just had a master's student that finished up where the idea was to take all of these different ideas and to try to fuse that data. So actually in each of these things, so at the front end, he's running a PDA filter to say, okay, is this consistent locally with what's happening? And then the idea is to fuse all of this at the back end using, again, some kind of PDA at the track level. So feature rating, again, we may have features that we track from, I guess, features to features. These are actually really good when you track features as opposed to just doing a background subtraction. So in other words, we're looking for, the backpack, or it's kind of hard to see that there's anything on that black object, but there's features that get tracked on this person, and they're pretty good at distinguishing, when you get close to another object, at continuing to distinguish that, the features don't jump over here to another person. So it's pretty good. This is the type of, so these are features that are being tracked from one to the next, and you kind of see, especially as they get close to each other, anyways, the type of thing that's going on. And then so we have multiple methods like this, and then we can actually combine these methods to, feature. I should have shown a video where feature matching does really bad if you go behind like trees and things like that, where there's lots of branches. The features get stuck on all of the branches, and so it has its pluses and minuses. Oh, here's a video. So when you this is actually a stationary video. So if you just do, for example, feature tracking, you get all these ghost tracks. So as people walk behind trees, there's a bunch of features that get just stuck on branches. And so when you combine these at a track level with, say, a PDA algorithm, at a track level, you can actually get rid of all of those ghost tracks. So this is the type of thing that we're doing, and so with a moving camera, these are the types of results that we get. And also, oh, by the way, background subtraction. So yeah, I'm not telling the full story. On background subtraction, if you're just doing background subtraction, when you're tracking somebody and they come along and then stop, and then start again, right? When they stop, you lose them. Right? But feature tracking actually does a really good job of keeping track of people, even though they stop. And so you really need multiple methods kind of at the front end to be able to track people when they stop, when they go behind, so these methods work well in different scenarios. Feature tracking works well when people stop and start. Background subtraction works pretty well when you're doing things like going behind, short occlusions or whatever. But you really need to combine the methods when you're doing something. I can't remember what I'm trying to show in this video. All right, so. Here's another thing that we're looking at. What do you do if, and we don't have a complete answer here on this one either. So if you're tracking targets from a UAV and you're really interested in where the target is on the ground, okay, there's a couple of things you could do. Number one, you could take all of your image features, track them in the image plane, and then you get these image tracks, and then what you do is you project those tracks down onto the world. And say, okay, maybe if you have a flat Earth assumption, the altitude, you could project those down and say, okay, this is the location on the ground. That's one idea. The other idea is to take your image features and project them down on the ground using a flat Earth model, where the models really make sense, right? The constant velocity, constant acceleration models make sense. Do your tracking algorithm down there and then get tracks in a 3D framework. And so we're really trying to figure out, what's the best way, which one's better. Here you have, so the advantage of doing this is that in the image plane, what the noise models are. They really are Gaussian, and they're relatively small, where once you project them down on the ground, you have all the noise that is involved in that transformation. If you have small roll and pitch errors, that gives you very large errors on the ground. And so the models are more correct in this framework, but the noise is unwieldy. Here you've got nice noise characteristics, but your motion models aren't very good. And so, we've been doing a bunch of work in this in this scenario where, and basically, one idea is to use a flat Earth assumption. And let's see, so you can't really see what's happening here, but if you do that, this is a gazebo simulation. It's basically showing, the actual track versus what you think the track is. And yeah, anyways, there's some error there. The video is not very good. And then the other idea that we're using is instead of doing this flat Earth assumption, what if we use some kind of visual odometry algorithm or some kind of, I guess, local SLAM algorithm to back out the position of the targets on the ground. And so I have a PhD student right now that's looking at several different, he was actually looking at EKF SLAM ideas locally to try to do this projection onto the ground, but is now looking at nonlinear observers. And I forget, oh yeah, okay, this is at least EKF target localization. So over time, we can localize these landmarks on the ground. Oh yeah, this is the scenario, or the situation is, so for these slides, so if you're trying to do like EKF SLAM, the EKF SLAM algorithm assumes that the landmarks are stationary. And so it works fairly well for stationary landmarks, but if the landmarks are moving, it doesn't work very well at all. So the idea is to, if you're trying to localize a moving target, what do you do? And so the basic idea is that we use the Ransac algorithm in the image plane. We then project that down into the world frame and say, okay, what are all of the landmarks close to where he's at? We then track, use EKF SLAM to track close stationary landmarks. And then we assume that the depth is what we don't have for the target. So then we assume that the depth is going to be, basically the average of the depth of the landmarks close to the moving target. And so we do, if you do that type of framework, or that type of algorithm, then we can get pretty good localization in terms of the depth. And this is just showing, it takes a little bit of time to initialize the algorithm. As soon as you initialize, because you're finding the features of the landmarks. So once you find the features of the landmarks, you initialize, you can find the target position. This is simulation data. And then now we're looking at doing that same type of thing in a nonlinear SLAM type framework. And when you do the nonlinear SLAM, again, you get things that look like this. All right, so, okay, so now what happens if you try to combine all this into a control algorithm? And again, this is ongoing work, so these particular slides just show what happens if you have your optical axis. This is some flight data that we took. So what happens if you just simply try to align the optical axis with the line of sight vector? So, well, this isn't particularly impressive looking, but I have to say I was so excited because this is closing the loop around so we have this recursive Ransac algorithm, but we had never really closed the loop around it. So we're actually closing the loop around the algorithm right now. And we're doing the tracking, plus we're actually following this guy using the tracking. Okay, so it's not as, yeah. I'm just going to move past this part. Okay, so we are doing some, in terms of flight tests, let me just talk a little bit about, we actually have a variety of different platforms, but this is one. We've got this 3DR Y6. We have a whole bunch of these around our lab, even though 3DR is now out of business. So once they break, we're, and in fact, we're taking these 3DR parts, and the number are shrinking because we're fixing parts, and so we lose vehicles as we fix other ones. But anyways, we have a Pixhawk with the Arducopter firmware, an NVIDIA TX2. This is a global shutter camera that's just pointing 45 degrees, it's pointing 45 degrees down. It's got about a 35-degree field of view. And, let's see. Actually, I was going to skip over those slides. Yeah, okay, so we've implemented this recursive Ransac algorithm. We actually have an implementation on a TX1, on a TX2. Of course, we have it also on a just standard i7 processor. We basically, all of the front-end vision processing is using OpenCV, and then we've got a C++ implementation of the recursive Ransac element at the back. Are you guys familiar with the TX2? I don't know if this is something you're using as well. So it's awesome. So if you implement recursive Ransac on, so for example, an i7 Bricks, this is an i7 processor, but it's an embedded framework. Lusk IX, this is my student's desktop computer with the GPU. An Odroid, this is the TX1, TX2. So basically, once you use the TX2 with the GPU utilization, you can do all sorts of things where you've got feature matching plus the homography. So if you put all these pieces together, it fits. So as long as the bars are underneath the dotted line, it runs real time. And so things fit nicely on a TX2. It runs, you can make things run, real time on the IX Bricks. You just can't have multiple front ends running at the same time. An Odroid, you can't do it at 10 hertz, even with just one framework. So you can do it at 2 hertz, which we've done. Okay, so anyways, lots of exciting opportunities for small UAS. And I don't know, any questions on this last little bit, the robust tracking stuff? Yes? So, so with those three UAVs, so you're talking about the video where we were doing collision avoidance. So there's, I have some slides on what we were doing there, but we have, there's basically, it's a two-step optimization algorithm. So there's an A-star algorithm kind of at the back end, and then it's kind of doing high-level waypoint, finding a waypoint path. And then once you find a waypoint path, then we have a trajectory algorithm that goes waypoint to waypoint that it takes into account vehicle dynamics. So, yes. So you were asking if we're using some kind of A-star algorithm, and the answer is yes, but in combination with it. Oh. Yeah. Right. Right. So, for example, visual flight rules where you need to pass to the right or whatever. Yes, we take those into account. Yeah. So the A-star algorithm has those constraints embedded into it. Right. Yes. So, yeah, we've actually thought about doing that sort of thing. What if we're going to track at night or whatever? But we haven't actually done it. We've played with infrared cameras before, and so I think that everything would work just fine on an infrared camera, but we haven't actually gone out and done it. Yeah, I mean, you have essentially the same types of characteristics that you do with an EO camera.
Just the background expression is easier.
Yeah. Yeah. Right. Were you just stretching? But now that you're stretching, you have to ask a question. No, I'm just kidding. Yeah. So yeah, that's a really good question. So I guess okay. So one of the things that happens when you close the loop. So the recursive Ransac algorithm. I didn't really talk about. Remember when there's a good track, we also put a track label on it. So it's really important that that track label stays constant, right? Because if you so one of the issues that we had the first time we closed the loop is you're tracking, and the track label would be like track 9 or whatever. And then if you lose it for a little bit of time, it basically, will sometimes put a different track label. It comes back and continues to track it, but it says, okay, now it's track 11. So, now you're still tracking track 9, right? Which is now a dead track. And so this is one of the issues that we've been thinking about. First of all, what do you do when the track label changes? So is this something where now the user has to get involved? Or do we say, okay, if a track goes away, but a new track is born close by, do we switch the label to that one? Which is what we're doing right now. So there's, but anyways, this is an issue, that if we want to do robust target tracking. So what we're going to do, I think our next step. So I've got a student working on saying, okay, suppose I have a bunch of people that are walking around, and I want to keep all of them, say, in the field of view, at least until some start to diverge or whatever. What do we do? And so the idea is that we'll have a bunch of tracks, and then maybe we'll try to track the mean of the tracks. And so their tracks starting and stopping may not be as big a deal. But anyways, we're kind of doing those sorts of things. But yeah, this idea of how do we make sure that we continue to track. So one of the challenges that I've given to my students, I really like to mountain bike. Is there mountain biking in Portugal? Okay. Anyways, so I've told them, I want to take my mountain bike, and I want you to, start tracking me, and I want to ride, through the mountains, through trees, up and down, where I come out of view and into view, but I'm mostly in view, and I want you to follow me and track me the whole time, like for a half an hour. So this is like the ultimate challenge, Can they track me mountain biking for a half an hour? And if we could get to that point, I think we'd be really excited. Okay, well, thank you all for listening. I really appreciate it.